about your book, the Scripture. In fact, that's where you should be spending your time anyway. If you want to learn the science, then fine. But don't find little tidbits of science and bring those up, because it makes intelligent people in my world push God away from them. It makes it easy for them to push Him away because of the non-science person using science to somehow prove what their point is, and that is that God exists. Okay, so here it is. We know that the proteoglycans themselves are held together by linker proteins within the cell. And there's a bunch of them, at least a dozen. There are probably more of these proteins that actually link the proteoglycans inside. So when you look inside the matrix, you see collagen and elastin and reticular fibers dominating the matrix. And then you see at high magnification, at scanning electron microscopy magnification, you see proteoglycans, proteins, core proteins, linker proteins, and glycosaminoglycans, and a bottle brush arrangement. And then you have other linker proteins that hold all of those proteoglycans together within the matrix. And those are called adhesion proteins. And two of them are fibronectin and laminin. These serve as connective tissue glue that allows the connective tissue cells to attach themselves to the matrix elements. So how does a fibroblast stay oriented? Fibronectin and laminin and many others are holding the proteoglycans together, and the collagen is playing a role in that as well. It's a very sophisticated network of proteins defining and creating the connective tissue of interest. Now, this is a picture of laminin that has been used by many people. I've heard several religious professionals do this. In fact, I had a guy call me a couple weeks ago. Wait, have you heard the story of laminin? I said, oh, Bert. So they read this verse out of Colossians where they say Christ is the invisible image and He existed before and He's the one who created. And then He existed, and here it is. He holds all creation together. And then the big punchline at the end of the presentation is, this is the protein that holds us together. And it looks like a cross. And all the audience, the non-science trained people in the audience, gasp with amazement, as though this somehow proves that Jesus existed, because laminin is in a cross-like arrangement. In fact, in scanning electron micrographs, laminin looks like this. So that's the first level right here. Laminin does not always look like this in a scanning electron micrograph. That's the first thing. But I would argue that laminin is not the most important protein. It's certainly not the most abundant. Fibronectin is just as important. It doesn't look like a cross. And I would say this. It is unfortunate that religious professionals want to take images, perhaps a beautiful image of a cross here and a sunset, to make people think about, religion and Christ and the crucifixion and all that, which is fine. And they want to somehow thrust that upon people as though that is proof of Christ's existence. And I would say, you need to stop talking. The science itself reveals a creator. We do not need to imagine images of crosses within connective tissues to do that. In fact, the Scripture itself says in Psalm 19 that the heavens are declaring the glory of God, their expanse is declaring the work of His hands. Paul echoes this in the book of Romans, and he says people are basically without excuse in believing that there is a God, because look around you. It would take someone without any insight whatsoever to make a basic look around and not think that somebody made all this. But today's science can do much better than that. The psalm goes on to say, this created order, the things of science, has no words. There is no speech, there is no words. So just because an individual looks and sees an image of a cross or looks and sees the beauty of nature, that should tell them there is a God. Fair enough. But those things don't say anything. The good news is there are, in fact, words that do say something. There's a book that records the creation event and a book that records and documents the existence of Christ and all that He did. I would much prefer if the non-science people would stop using images, supposed cross images from connective tissue, and spend more of their time revealing the story as it is documented in reliable form in the text. Now, science, as you guys have already learned, can do much better. For example, any person who's had an introductory class with me knows that it has had a real impact on science to learn about the structure of DNA. There are evolutionary biologists, many of them. There are atheists, many of them, who are left now with thrusting life itself as the production of an alien race because of the observation of the non-specificity of the glycosidic bond. So you want to talk about the science, this is where you should begin. The science community recognizes that the order of the letters in the DNA molecule is the language of life. And describing how this language was put in place is best described as the work of an author. Someone wrote this language. Here's another level you've already seen this semester. This is a cilia that is extending, and we've talked about this 9+2 arrangement of the anatomy of the cilia on the outside of the paramecium, on the outside of the pseudostratified columnar cells. And I would say, let's talk about the best explanation for how a cilium came to be. We can do this with science. We have abilities in the laboratory to test these things. So if you're going to describe how the structure came to be, then you need to describe precursors. You need to be able to back this thing up in time. You need to be able to back this thing up in terms of its production. And we know now how the cilia is produced, and we know now what happens whenever you modify proteins in a cilium. And those observations do not point to random mutation. Those things point to the work of a designer. The best explanation for this anatomy is not random mutation followed by natural selection. The best explanation for this is it was constructed this way the first time. Otherwise, it doesn't work. Something that Michael Behe calls irreducible complexity. If you do knockout stuff on these and you modify one of these proteins, you don't get a cilium that works less efficiently. You get a cilium that unravels and doesn't work at all. So either all the proteins are put together to build this structure so that it functions in its full form, or it doesn't work at all. We can test that. So how do you explain that? What is the best explanation? The word in science we use is parsimony. The easiest explanation for what we see. And it's not natural selection. This is a picture of a flagella. It is made from dozens of proteins. So much more sophisticated than a cilium. This thing works like a little engine, a propeller. It has all kinds of pieces and parts of a propeller engine that you would find on an outboard engine running a bass boat. Same thing applies here. We know the construction mechanism that was put this together. How do you walk this backwards? If you begin to modify the proteins or any of the structural pieces that are used to build them, to put them together, you have a flagella that won't function. Now, Ken Brown has suggested a precursor protein for one of the pieces in this thing It's part of a type 3 secretory system. You can see this mentioned here. And in just the last couple of years, it has been demonstrated that that type 3 secretory system is actually dates to a date earlier than the flagella itself. Now, you're not going to find this in your textbook. But when I pointed this out to the group in New Orleans, I got stone cold silence everywhere. What is the best explanation? How do we describe something like this? A machine that is functioning. All of its parts have to be constructed and put together in a very particular and precise way in the cell. This is the work of a designer. You don't open the hood of an automobile and look inside and say, accident. It takes a great deal of work in the scientific community today to try to convince people that what they are seeing is what they are seeing. Because there's blinders in front of their eyes, and they will not accept the fact that these things appear. The best explanation we have for these things is, in fact, the work of a designer. This will come up next semester. So from the DNA to the simple protein-built structure, to the complex protein-built structure, to the mechanism. And there are dozens and dozens of these. You will learn many of them in human physiology next semester, where there is a sequence of events. Now, 5 of them are shown here for vision, but if you count them in a biochemistry text, you can get somewhere between 18 and 25 separate molecular steps. So light hits it, and then you proceed. Molecular mechanisms. Everybody says, well, how did I see? Light hit my retina, and the retina sent a signal to my brain. Really? That will no longer do. In today's world, what happens when light hits the retina? A series of 18 to 25 molecular steps occur. What happens if one of the molecules in that sequence is removed? Do you get an organism, as a Darwinian model would suggest, that sees less, that has less ability? You know, they lose color, they lose depth, they lose peripheral. Is there anything that we can use in the visual world today to describe what happens whenever you alter one of these steps? No. When you alter one, you don't get an organism that sees less. You get total blindness. And so what that means is the mechanism itself for vision to ever have occurred the first time, this mechanism has to be in place. Okay, so I'm telling you all you guys this stuff so that you can see the power of learning the science. Don't play with the images. If you want to play with images, religion professionals, I would advise you stay with the text and keep your observations out of the world of science. Because the science actually does suggest that we have a creator. Okay, so do better. All right, here are the cell types for the connective tissue. So we did the unstructured material, the ground substance. We talked about the proteins there. The next big thing we had on there were fibers, collagen, elastin, reticular fibers, and we're going to show you those as well. This picture talks about the cell types. So the big 4 on the slide that we saw before were, I know you don't remember them, here they are: connective tissue proper, cartilage, bone, and blood. These are the 4 bigs for connective tissues. So this picture illustrates them for you and the types of tissues we'll want to look at. The fibroblast is the major cell-producing, matrix-producing cell of the connective tissue propers, and they include areolar, adipose, reticular, regular, irregular, elastic. So these are the ones we're going to look at right here. The chondroblast is the major producer of the cartilage material, and they're the 3 cartilage types we'll look at: hyaline, fibro, and elastic. The osteoblasts produce bone, and I'm going to describe compact and spongy bone for you. And then blood. Does that surprise you? If we started class today and I would have said, answer this question: is blood a tissue? Would you have said blood's a tissue? Be honest. Blood's a liquid, yeah? Okay, how do we define a tissue? A connective tissue in the body is a matrix, yeah? Unstructured matrix. It is fibers, and it is cells. Now, you know about blood. What is the unstructured matrix of blood? In a blood sample, you have blood. What is the unstructured matrix? What do we call the stuff on the outsides of the cells in blood? It's mostly water. What is it called? You go to the doctor, you go to the clinic to give blood, and they put your red cells back in you. They just took what? They took the plasma, the unstructured stuff. So it has an unstructured extracellular matrix. What are the cells? Red blood cells, white blood cells, platelets, cell fragments, right? Fibers. The fibers I mentioned are collagen, elastin, and reticular fibers. Are there any fibers in blood? I would say that would be very dangerous, wouldn't you? If blood is going to continue to move through my body, I don't need fibers in there, right? So I take the students down to the cadaver lab, and I say, let's take the heart out of the cadaver today. So they cut through the pericardium, and they cut around the major blood vessels, and they remove the heart. And they've done the sheep heart here. And the human heart and the sheep heart look essentially identical. But the sheep hearts they do in the lab here, they go, oh, I can see everything. There are the valve cusps and the chordae tendineae, papillary muscles, moderator band, the right ventricle. I can see all that. It's beautiful. I cut it open. And I cut this human heart open, and I don't see anything. And so the only way I can see anything in there is I've got to dig all of this tissue out of there. What is all that? It's blood. And what has happened to that blood? It's clotted. Yeah. So blood does in fact have fibers. It's just that they're not normally come out of solution. It happens when the blood clots. So the best way to describe blood as a connective tissue is to say it looks more like a tissue the way we think of tissues when it's clotted. You can see this in a cadaver. The blood is a tissue. Okay, so here's the first one, connective tissue proper. It's the prototype, and you can see a lot of things that I've been describing. You can see collagen fibers, these dark red things. You can see elastic fibers, these little spidery looking things, little thin lines. You can see the fibroblast nuclei. There are also plasma cells in this guy right here as well. So the connective tissue proper here is a prototype. It has cells in it, but would you guys define the loose connective tissue? Would you define this stuff by its cells? No. How would you define this? Why do we call it loose?
Is it not connected to a cell?
I'm just thinking appearance. Why would you call it loose? The collagen and the elastic fibers, they're not all, yeah? It's loose. Now this stuff is really important. The loose connective tissue is widely distributed under the epithelium of the body. So loose irregular connective tissue is part of the fascial surfaces that cover organs, that create compartments in the human body. This stuff forms what is called the lamina propria of mucous membranes. So these will come up as we get to systems, these lamina propria pieces. This stuff packages organs and surrounds capillaries. The loose areolar connective tissue is a significant part of the fascia that packages not only organs but also the entire body. So, not this coming Thursday, bone test, right? The next one, you're going to start skinning your cat. And all of you are going to have by that time the dissection instructions with you. Everybody will bring those with you 2 weeks away from yesterday, and you'll start the dissection. And then you'll pull the skin off the cat, and you'll look at it, and then you'll look in your book or online at the picture, and you're going to be trying to identify the pectoralis brachialis, the pectoralis major and minor, and the xiphohumerales, external obliques, rectus abdominis. All these ventral muscles, you're going to be saying, I want to identify them. You look at the book, and they're beautiful. And you look at the cat, and they all look like they're one big muscle. Why? Because there is a fascial covering. So we call the hypodermis the superficial fascia, and the next one we call the deep fascia. And this deep fascia covers the muscles. It packages them. Part of its anatomy is this tissue, areolar connective tissue. So that's what I want you to think. I'm going to have to pull the fascia, the areolar connective tissue, off of this muscle so that I can see it. That will be your job. That's really the major job of the test on muscles and bones that comes after your bone test. To get enough of the fascia off so that you can define the borders of the muscles. All right, here's the next one, adipose tissue. This stuff is under the skin. We'll learn the skin has two major layers, epidermis and dermis. And this we call, normally books will call this the superficial fascia. So anywhere on your body you can go, if you can pinch the skin anywhere on your body, you can assume, watch it, fancy formula, that the superficial fascia, which is adipose, makes up about half of that width. Yeah? It's adipose tissue. And it's regulated by both the nervous system and the endocrine system. So sex hormones, estrogen, estradiol 17, beta, and testosterone play a role in its distribution. Normally, ladies have a little thicker hypodermis, which is what this under the skin part is. The hypodermis, the superficial fascia underneath the skin. Ladies have a little more than men. It's also distributed in various places. So the breast tissue tends to accumulate this adipose tissue. In men, as the hormonal levels change, as a man gets older, around the midsection, the adipose tissue begins to develop more. So it's time sensitive, it's hormone sensitive. It looks like this, adipose tissue, under the skin. It's around the kidneys. Have y'all heard this before? Around the kidneys. Why would that be significant? Why is it significant that there is adipose tissue around my kidneys? What do you know about the kidneys already?
Something about the sac.
You're outside of it.
Outside of what, Jared? They are outside of the peritoneum, yes?
Yeah.
They're retroperitoneal, which means they need protection. Would this stuff do? Yeah. It also shocks students. It's not mentioned here, but also shocks students when they're doing a thoracic dissection. And you'll see it on your cats as well, but humans especially. When you cut through the thorax and open up the thorax and look at the heart, even in an individual who is not obese, you will find gobs of fat around the heart. Protection. Okay, here's the next one. This is loose areolar connective tissue, the reticular variety, and this stuff is found in lymphatic organs, bone marrow, and spleen. So this is a little different variety of collagen. I mentioned this to you just a moment ago. This scaffolding collagen of the reticular connective tissue. So this is reticular. So where would you find this stuff? In lymphoid organs like nodes and bone marrow. Okay, so one of the things that we will see in the immune system anatomy, this will be in the last test section of this semester, is the structure of a lymph node. And they have some telltale anatomical things in them, these lymph nodes do, that will help us compare other lymphatic structures to them. But one of the things that jumps out immediately is the interlacing of what appears to be some kind of skeleton or septa that laces through the organ itself. And the closer you get to that skeleton, the higher the magnification, the more you can make out the scaffolding of this protein in the tissue. The cells there, so in lymph nodes, the big ticket items are the white blood cells, the T lymphocytes and the B lymphocytes. They all appear to be lined up on that scaffolding, as though the scaffolding is used as a structure to be used in their development. And that's exactly what happens. And so the first introduction here you're getting to lymphatic structures is there is a skeleton, a network of collagenous material called reticular connective tissue that builds the inside of that lymph node. Same thing you would see in a section of bone marrow. Now, that slide description right there is not quite good enough. Because as it turns out in our bones, which you will learn Wednesday next week, I think, I may get there, you will learn there is that bones, in fact, have two kinds of marrow in them once they have finished their development. In the ends of the long bones, you have red bone marrow. But through the shaft of the long bone, it's yellow. If you look close up at the yellow marrow, it looks like this. The shafts, the cavity in the shafts of your bones is filled with adipose tissue. This is the stuff that you see in the ends of the bones. So you will also learn now and later that the ends of the bones are where you find the tissue that produces blood cells. The red bone marrow. In the language that I'm going to use in just a moment, the hematopoietic stem cells that make the blood cells. This is where they come from. They come out of this tissue in the red bone marrow. And that stuff is found in the epiphyses and the ends of the long bones. And it looks like this. So did you hear that twice? Did you hear the development of white blood cells here in the reticular tissue of the lymph node? Did you hear the development of blood cells in the red bone marrow here? Reticular connective tissue. You should have. That's what you should have heard. And then the spleen, this is actually a section of spleen here. The spleen itself is made up of a couple of different types of pulp. There is a scaffolding for the destruction of red cells in the spleen, which is why it's called the red blood cell graveyard. And there's also a scaffolding like the lymph nodes have within the spleen as well. So it's just another example of where you would find reticular connective tissue. We will, I promise, spend more time on this one in this text section. And in the last section of the course, I'll show you lymph nodes and spleen again. So it's not the last time you'll see it. Okay? This is an example of dense, regular connective tissue. It's the one that I used with you when I was introducing the importance of using proteins to describe the anatomy. And you can see why it's called dense regular, because the arrangement of the collagen protein is a regular arrangement. This is the tissue of ligaments and tendons and aponeuroses. Now, most young people come to me knowing that a ligament attaches a bone to a bone, and a tendon attaches a muscle to a bone. Not many come to me knowing what an aponeurosis is. No? Nobody nodding? Okay, so the first aponeurosis we'll see in this class is a sheet of collagenous, dense, regular connective tissue that extends from a muscle that sits right here, called the frontalis, across the top of your head and attaches to a muscle that sits right here called the occipitalis. Now you've been learning skull, right? Frontalis, occipitalis, those names make sense? Okay. The connective tissue sheet that connects them is called the gallia aponeurotica. The aponeurosis. So you can see them attached. As it turns out, there is no muscle here. That's bone. So you can see the neurotica here when I do this. Can you see it? Attaching from the frontalis to the occipitalis. That's the first aponeurosis. If you cut it and look at it under a microscope, it looks like this. It looks like a tendon. It looks like a tendon. It looks like a ligament. This stuff, as it turns out, is extremely strong. The regular arrangement of collagen and tendons and ligaments is stronger. Now think about this. It is a living macromolecule that has been arranged like this in the tissue. And it is, gram for gram, stronger than steel. So when somebody tears their anterior cruciate ligament with a hyperextension of the knee, they put some torque on that bad boy to tear it. These very strong tissues. We'll stop with this one for today. This is dense irregular connective tissue. Can you tell me why I would call this one irregular and the other one regular? Why, Jared?
It's not sheeted.
Okay.
It's not organized.
It's not regular, right? What's not regular?
Looks like the extracellular matrix. It's not-
Yeah. Is it the cells that aren't regular? No, it's the arrangement of the proteins. Now, this stuff is common in the dermis of the skin. It is common in the submucosa of the GI tract. It is common in the fibrous capsules of organs and joints. We'll want to distinguish between those. So don't just take that lightly, okay? We're going to talk about dermis again in this test section. But later, as we start to get to the synovial joints, I'm going to point this out to you. In a synovial joint, there are, in fact, tendons and ligaments that we'll need to know the names of. But in addition to learning the tendons and ligaments and how they're connected, each of these movable joints, it has a package. The joint itself lives in a house. There's a capsule that keeps the fluid in there. If you want to get a sample of the fluid, you'd have to puncture through it. This is the stuff that makes the joint capsules. It looks different histologically from the tendons and the ligaments of the joint. Okay. We will pick up with cartilage on Wednesday.